Fantastic. Morning, everyone. Just to let you know, this lecture is being recorded. So we started working on integer and mixed integer linear programs last week. We're going to continue this week, and next week we're going to learn how we can. There are like different methods, as I told you, to solve or deal with integer and mixed integer linear programs. Next week we will cover one of essentially one of the famous methods that we can use to tackle integer and mixed integer linear programs. Today we are going to continue with solving examples of mixed integer linear programs or integer linear programs. And there are some logical statements that we will learn at the very end, like the one that we covered in the workshop last week, the one that we saw for either or constraints. If we have two different constraints that we want them to be mutually exclusive, so not both of them at the same time, then we would use that essential template to write the constraints in a way that only one of them will happen at a time. Let's start with the problem that we have today. This is the problem that we're going to work on. I will give you a few minutes. Please read the problem. Try to understand the problem. Try to define the decision variables for yourself, and as much as you can, just proceed, and then I will solve the problem. So if you read the problem, do you want to write on the chat box what do you think? What are the decision variables? What are the types of how many decision variables we need, or what are the types of decision variables? Just write in the chat box. No one wants to write, or you hear me, right? You hear and you can say the slides also. Okay, that's fantastic. Yes, thank you. Number of each box produced, amount of box one. Okay, 7 decision variables. Yeah, fantastic. Y1 to Y7 produce or not box n. Okay, that's very good. For the chat box, it's more than enough to write it this way. I'm pretty sure you know how you have to define it properly. Yes, that's fantastic. Let me read the problem for those who couldn't read or didn't understand. We have a company who sells 7 types of boxes. These boxes are ranging in volume from 17 to 33 cubic feet. The demand and size of each box type are given in the table that we have here. So these are the boxes that we have. Box 1, for instance, its size is 33, and the demand for this box is 400. We have box 2, the size is 30, and the demand is 300. It goes until box 7, where the size is 17 and the demand is 200. You can see that the boxes are ordered in a non-increasing order of the sizes. So we start from 33, goes to 30, 26, 24, 19, 18, and 17. And demands are given, so demands are independent from the order of the sizes. The cost in dollars of producing each box is equal to the box's volume. So for instance, for box 1, the cost of producing this box is equal to 33, which is its size. Moreover, a fixed cost of 1000 is incurred to produce any of a box type. So if you want to produce any of these boxes, then you have to pay $1,000. This is the fixed cost. This is like the machinery that we had for shirt, short, and pants example, or yeah, that's a fixed cost essentially. So if you have the machine to produce the shirt, then you can produce the shirt. That's the same. So if you buy the machines or whatsoever that you need to produce this box, which costs you 1,000, then you can produce them. All demand should be met. So if demand for box 1 is 400, we have to essentially satisfy that. So this gives you an idea of how you have to write the demand constraint. Here, if the company desires, a demand for a box may be satisfied by a box of larger size. So if someone comes with a demand of box 2, for instance, the demand of box 2 is not 300. I mean, it is 300, sorry. The demand of box 2, which is 300, it can be satisfied by box 1 because it is bigger. It's not something that we wanted. Why we don't want this? It's not something. Otherwise, if it was the case, you would just go and only produce box 1, because with box 1 you can satisfy the demand of box 2, 3, 4, 5, 6, 7, including itself. Box 2 can satisfy demand of box 2, 3, 4, 5, 6. 3 can satisfy 3, 4, 5, 6. 4 can, and so on and so forth. As it is written, Sebastian said, it is more expensive. If it wasn't, because the size is 33, obviously the cost is also 33. We know there is a fixed cost, so if you want to, why it should be something that we want to do, we won't prefer this maybe by the first look, that we don't want to satisfy all demands by box 1 because it is more expensive than box 7, for instance. The price of box 7 is 17 the cost, but for box 1 it is 33. We don't want to do this because the cost is more. But why it should be something that we can look into? Why it should be something that we may practice? We say that, oh, there is a demand for box 5. We know that its price is 90, but we decide to satisfy demand of box 5 by box 4 because box 4 is larger, so it is possible to do that. But we do that again, as Sebastian said, yeah, there is a fixed cost of producing box 5. Maybe the price economically feasible. Do you remember this that we had in the core example last week? So it might not be economically feasible to do that. That's why we may decide to satisfy the demand of smaller box by a larger one, even though we know that it is more expensive. If box type 5 and 7 are manufactured, then the total fixed cost is 1500 instead of 2000. So if you produce both these boxes, the fixed cost goes down to 1500 rather than 2000. This is because the machines are similar to each other and those stuff. The company must manufacture at least 5 boxes, types of boxes here. Formulate a mixed integer linear program to minimize the total cost of meeting the demand of boxes. This is the problem that we have. Now, we have to see how we can, what the cost comes from, essentially. Okay. So some of you said that it is the decision of whether or not we are going to produce each of the boxes, and there is another decision variable that we will see now. So parameters that we have for this problem. There are some parameters that we have. The first parameter here is SI, which is the size of the boxes. We know the sizes of the boxes, which gives us the cost of production of each of these boxes. So SI is the size of box I, and I itself is from 1 to 7. DI is the demand of box I, and again I goes from 1 to 7. Now we have to define the decision variables. XI is amount of box I. So the number of box I, maybe that's a better definition, but it doesn't really matter. So xi is amount of box I, where I is from 1 to 7. Then we have yi, which is 1 if box I is produced, and otherwise it is equal to 0. Do you think it is enough to build the model? Go back to the previous slide. Looking at this one. Are these decision variables enough to build the model? Just knowing how many of each of the boxes we are going to produce, and whether or not we are going to produce. Whether or not decision is there because there is a fixed cost. If there is a fixed cost, then you have to have a decision variable to make sure that you add it to the objective function. The second decision variable is the number of each of the boxes which should be produced. What else should be there as a decision variable? Are these enough to build the model to satisfy everything that we have in the variable statement, the written statement? What do you think? I want you to think about that. What do you think? Any idea? The fixed cost changes if box 5 and 6. Okay, that's a good point, that we have to somehow incorporate this. That's a very good point, because DC is something which has something to do with the objective function, and the objective function includes the decision variable. So there should be something there. Fixed cost should be added as well. Yes, fixed cost will be added using the void decision variable that we introduce here. That's the objective function. But my question is, if we need any other sets of decision variables here? Yes, we need. If you're going to answer the question, if you're going to essentially, if you're allowed to satisfy demand of a box by a larger box, we have to answer at the end of the day. For satisfying the demand of a specific box, are we going to use itself to satisfy it, or one more larger one, another larger one? So if you're talking about box 4, we can satisfy its demand by 3, 2, and 1. So the 700, how much of the 700 is satisfied by box 4? How much box 3? How much of box 2? And how much of box 1 are used to satisfy the 700? So we need to define a new decision variable, which is amount of box I used to satisfy demand of box J. I and J are essentially from 1 to 7, but we know that we are not allowed to use demand box 2 to satisfy demand of box 1, but the other way around is essentially allowed. Now the objective function is the total cost that we have. The total cost here, the first part is the variable cost of producing these boxes, xi. How many of each of these box i's should be produced? Si is the size or the cost as well. So it is summation of si's multiplied by xi's. Summation is over I. Remember that when you have an index, you have to make sure that that index is included in the that index has a range or something. So you have to make sure that that index is somehow defined. The second part is the fixed cost of production of these boxes. So 1000 multiplied by summation of yi, and again y is from 1 to 7. Do you have any other costs that should be added to the objective function? What do you think? It was mentioned in the chat box that this part, if both box types 5 and 7 are manufactured, then the total cost goes down from 2000 to 1500. So this if yi essentially y5 and y7, both of them are equal to 1, then I want this 1000 plus 1000 to go down to 1500. So how are we going to do that? Is it possible to do it using the decision variables that we have? Is it possible to use xi, yi, and xij to make sure that when y5 and y7 are equal to 1, then the total cost is not 1,000 plus 1,000, but it is 1,500. It's not possible, or if it is, it's not easy to formulate it. So what we do is we define a new decision variable, which is W, and it is equal to 1 if box 5 and 7 are produced, and otherwise it is equal to 0. So when y is equal to 1, then a cost of 500 should be deducted from this total cost. Does it make sense? 1,000 multiplied by y1 plus 1,000 multiplied by y2, y3, 4, 5, 6, 7. When y5 and y7 are equal to 1, 1,000 plus 1,000 will be added. But what I want to do is I want to bring it down to 1,500, so a 500 should be deducted. That's why I have this W, and W is equal to 1. If it is equal to 1, 1,000 plus 1,000 minus 500 gives us 1,500 as the cost of production of these two. Okay? Does it make sense? Because I already have them here, I have to deduct this 500 to make it essentially 1,500 rather than 2,000 that we have. Okay? Do you have any questions until now? Is it clear? Okay. Now, we have different relationship between these decision variables. So we have xi, which is the number of the amount of the boxes that we have to produce, y, whether or not we are producing each of these decision each of these boxes, zij, which is how many of demand of essentially demand of amount of box I used to satisfy demand of box j. And then we have W. You can see here that you don't have to have all decision variables in the objective function, but the objective function always includes decision variables. Okay. So here you can see that xi, which has a direct impact on the cost, is in the objective function. Yi, which has a direct impact on the total cost, is in the objective function. W, which has a direct impact on cost, is in the objective function. But Zij is not in the objective function because we only use this in the constraints. How we're going to use this, how we are going to write the relationship between x and z decision variable. X was the number of boxes to be produced, and z essentially shows how many of these boxes are used to satisfy itself or other boxes. Just looking at the chat box, when it is just yi, the cost is 1,000, and when yij, then the cost is 2,000, and then just subtracts. You don't have yij? So when it is yi, that's the direct fixed cost of each of the products. What the question says is that when you produce 5 and 7 at the same time, you expect the total fixed cost to become 1,000 plus 1,000, which is 2,000. But it says that because they're similar to each other, you don't need to change the production line, those stuff. The total cost becomes 500. Okay, that's why we introduce this new decision variable, which is W, and this W is equal to 1 when both of them are produced. If both of these boxes are produced, the total cost, when both of them are produced, essentially Y5 and Y7 are equal to 1, and the total cost becomes 1,000 plus 1,000, which is 2,000. So when W is equal to 1, I want to subtract this 500 from 2,000 to bring down the cost to 500. Okay, fantastic. Now, the relationship between x and y. X is the number of boxes that we are going to produce from each of the types, and Zij is the number of boxes that we are going to use to satisfy each of the boxes that we have. And we have this this requirement that only a larger box can be used to satisfy smaller box demand. Okay. Do you see that this is correct? We have summation of Zij equal to Xi. Does make sense? Just have a look at this and see how it works. So what we have here is, let me just have my pen. Okay. So let's say I is equal to 2. Okay. What we want to write here is x2 is the total. It's a lot. Let me just not x2 because that's another way around. Pen. Now let's say I is equal to 6. When I is equal to 6, and remember how did we define Zij? So it is um, amount of box I, which is used to satisfy the demand of box J. Okay, so when I is equal to 6, if we go back, we can use this one, box 6, to satisfy itself and 7, because a larger one can be used to satisfy demand of a smaller one. So when I is equal to 6, essentially on the left hand, on the right hand side, we have 6, and here on the left hand side, you see that this summation starts from J and it goes to 7. So what we can write here on the left hand side is Z, it's IJ, right? 6, 1 plus Z62 plus Z63 plus Z64 plus Z65 plus Z66 plus Z67, right? This is what we can write, but if this was not one of the conditions that we have, if the company desires a demand of a box may be satisfied by a larger box, this is what we have in the left hand side. But as we know, you can't do this. 6 cannot be used to satisfy the demand of 1. 6 cannot be used to satisfy the demand of 2. 6 cannot be used to satisfy demand of 3, 4, and 5. Only these ones are allowed. That's why you can see that the summation here says that you have Z I, J, I is equal to 6, and J starts from I. So it's 6, 6, and it goes to 7. 6, 7 is equal to x6. Essentially, this gives you the total amount of box 6 which is produced, and the left hand side is the portion of the 6 which is used to satisfy demand of 6, the portion of the 6 which is used to satisfy demand of 7. Okay, this makes sense? Does make sense? Looking at the chat, but please repeat again. Which part you want me to repeat? Okay, let me just erase all the ink. We are in the constraint now. Let me just explain the constraint, and then we will move to the. I'll go back to the it will be considering book 6. It's one example. So as you see here, we have summation of Zij. J starts from I to 7. This is equal to xi, okay? And I goes from 1 to 7. So how many constants we'll have here? If you write them, the open form, how many different constants we will have here? Write in the chat box for me. How many constants we will have? 7, right? When I is equal to 1, we have a constraint. When I is equal to 2, 3, 4, 5, 6, 7, okay? I wrote only 6 as an example because it was easy. So when you start from I equal to 1, let's say, okay? When I is equal to 1, the right-hand side is x1. You want to write a constraint to satisfy this. It says that you can satisfy demand of a box by a larger one. So if you're talking about box 1, which box types can be satisfied by box 1? All of them. You can satisfy demand of box 1 by box 1, box 2 by box 1, box 3 by box 1, and so on. Okay? So the left-hand side becomes Z11 plus Z12 plus Z13 plus Z14 plus Z15, Z16 plus Z17. Okay, this is the total number of box 1 that we produced, and the left hand side is how many of this box 6, box 1, which are produced, are going to satisfy the demand of box 1, the demand of box 2, the demand of box 3, 4, 5, 6, and 7. Okay, when I is equal to 2, the right hand side is x2, the number of box 2 that you produce. You can use box 2 to satisfy demand of box 2, 3, 4, 5, 6, and 7. So you start from Z 2, 2, 2, 3, 2, 4, 2, 5, 2, 6, 2, 7. This is what is written here. J starts from I. When I is equal to 2, you start from 2, 2, you go to 2, 7. When I is equal to 3, you start from 3, 3, you go until 3, 7. Okay, does make sense now? Okay, great. When you have the closed form of constraint, I would always recommend you to um, write down the open form so that you can see what are I's, what are J's, those stuff. Okay, this is the first constraint that we have. Now, moving forward, we have the demand constraint. Forget about this part. It's something which remains here. Now, the demand constraint. The first constraint that we wrote is essentially the relationship between x and z. Now we have to write the demand constraint. The demand constraint here, so you can see, based on what we wrote initially, the demand of a constraint, the demand of a box may be satisfied by another box, which is a bigger one. That's why we have to use Zij. So what we write here again, J is, we use J here to, because we have Zij. The demand of each of the boxes, again, J goes from 1 to 7. How many constraints we have here? Again, we have 7 constraints because we have to have a demand constraint for each of the boxes that we have. And then the left-hand side is which ones we can use to satisfy the demand. In the previous one, it was summation of Zij. J was from I to 7 equal to x I. Now you can see that here we have the summation of Zij. I starts from 1, but it goes until J only. Because this is the other way around. Here we would just write the ones that we could use to satisfy the others. Now here we have to see for demand of this J, which ones can be used to satisfy this. For instance, when J is equal to, let's say 2, for box 2, if you look at this one again, box 2. Let me erase everything that I have here. Now, here, we're talking about box 2 and demand of box 2 can be satisfied by which types? We can use box 2 to satisfy this one and box 1 to satisfy it. Now, I'm going back to this constraint. Here, J is equal to 2. D2. Demand of the second box can be satisfied by itself plus, let me put it the other way around, and also 1 can be used to satisfy demand of box 2. So you see I starts from 1, it goes until J, which is equal to 2. We can write the same for 3. When you're talking about box 3, you can use 1 to satisfy demand of 3, you can use 2 to satisfy demand of 3, and you can use 3 to satisfy demand of 3. This is because a larger box can be used to satisfy demand of a smaller one. I'm just checking the chat box. How to write the constraints in IJ form for the constraints you told before? I'm not sure if I understand what you mean. So we have RJ constraints. I mean, you can write the constraints like this. You don't have to write them like this. You can write all constraints separately. For 1, for 2, 3, 4, 5, 6, you can write them as you want. Once you write them all, you will see how you have to write this one. So I didn't have this one first and then conclude this one. I had these ones for j equal to 1, 2, 3, 4, 5, 6, 7, and then I wrote this one because I concluded from the ones that I wrote. That's the other way around. I don't know why these ones remain here. Now we have the fixed charge constraint. Again, that's the same. If you remember for the problem that we had for shared short and pans, we wanted to make sure that if the machine is there, then we can produce the we could produce the product. Okay, we are doing the same here. We want to make sure, because there is a fixed cost associated with each of these products, we want to make sure that when y is equal to 0, there is no production of that type of the box. Why we want this? Because if you do it another way around, I mean, when this is equal to 0, x is, when y is equal to 0, when x is a positive value, you will have a wrong total cost. Essentially, your optimal solution will be wrong, as we showed you last week in the lecture. And the other way around, when y is equal to 1, which means that we pay the fixed cost, now we can produce x, and it can take a value which is as much as a big number of m. So when y is equal to 0, x should be equal to 0. When y is equal to 1, we want xi to be less than or equal to m. This is what we covered last week. What is the reasonable value for m? What do you think? What should be the value of m? How big m should be? Yes, we know m can be m can be a very big number. But what can be m here? Demand. What you mean by demand? For box 1, is it demand of box 1? If we go back to the previous one. So for x1 less than or equal to my1, do you think that m should be 400? Any other thought? x1 less than or equal to my1, and demand of the first type of the box is 400. Do you think that this should be m? The sum of all boxes demand. Yes, that should be the case, because when we have this constraint here, you may decide to, at the end of the day, there is a case that you may decide to use only box 1 to satisfy demand of box 1, 2, 3, 4, 5, 6, and 7. So box 1, x1, should be allowed to be as big as the total demand of these boxes, because this is what can happen. For box 2, it is demand of box 2 plus everything less than that. For box 3 itself and everything less than that. Okay, so the number of each of the boxes that we can produce here, based on the constraint of one box can be used to satisfy the smaller box demand. We have to find the total number of demand that it can satisfy, and that one becomes big M. But at least 5 types of the boxes must be chosen. Yeah, that's all right. But you don't know which ones, right? The question is that, yes, that's a valid objection, that you can't use only box 1 to satisfy demand of all of them, because at least 5 of them should produce. Yes, that's a valid point. But I don't know which 5 will be, right? That's why I will take the total demand here. One way is you go with different combinations of 5s, and among them, we'll take the one which is the highest one, and it becomes A. So even if we select box 1, we have to select 4 others. Yes, as I said, that won't happen. What I said, that only one will be used to satisfy demand of all other boxes. But as we don't know which 5 will be produced, then I don't know what is the summation of those demand of those 5 boxes. That's why you either go with the demand of the total demand of all boxes that we have, or you will go with combinations of 5. 1, 2, 3, 4, 5, for instance. You take the total demand, whatever it is, save it. 1, 2, 3, 4, 6. Now go on, and you can see this a lot of them that you have, right? 5 out of 7. It's a lot of different combinations that you have. So it's better to have the total demand. What is the difference between the first two constraints? It both tells you it both tells you we need to satisfy the demand, right? So why we need to separate into two constraints? No, there are different constraints. The first one makes sure that there is a relationship between xi and zi. If you don't have this one, you won't have a correct x value. If you don't have this one, you won't have a correct x value, how many of each of the boxes you have to produce. Okay, so the first one is the relationship that xi has with zij, and this one is to satisfy the demand. So there are different constraints. They don't imply the same. This one says that you have to satisfy demand. This is essentially an input. dj is noun, but here xi and zij, both of them are on noun. So we want to see how many of other boxes are used to satisfy demand of another one. And then we can use this to make sure that the demand is satisfied. Maybe 5 boxes with max demand. Yes, that's something which is valid. Yeah, of course. So we're still talking about big M. Rather than using the total demand of all boxes, you can use the 5 which are the maximum, with maximum demand. Okay, but still, it is 5. It's something that you can do when you have a higher number. Still, you have for 5 with the highest one. That's fine. Yeah, 5 with the highest one should be fine. Yeah. It's better than, so I mean, there is no there is not a massive difference if you have the BM as 1000 or 2000, but it matters when it is 1000 and you change it to 1 billion. Okay, but if you produce all 7 boxes, the whole point is we started this discussion because there is a concern which says that at least 5 should be at least 5, or at most it was, sorry, the company must at least 5 of them. Okay, it's at least 5 of them. Okay, yes, it's not exactly 5 of them. So it goes to sorry for that. It says at least 5 of them. So you may go with 7 of them, 6 of them. So there are different cases. You got the point what I mean. I don't want to have M as 1 billion, but having like 1000 and 2000, it's not a massive difference. So that should be fine. Let me continue this one. We have the fixed charge, as I said. When y is equal to 0, x should be equal to 0. When y is equal to 1, which means that we consider we are producing this this box, then x should be as big as it can be, or it should be. Now, relationship between y and w. Can you write this for me? Can you think about this for a few minutes? I want to write a constraint which imposes the relationship between y and w. Y and w, we have it here. If both box type 5 and 7 are manufactured, then the total fixed cost is 1500 instead of 2000. How I'm going to write this as a constraint. And I want to make sure that when y5 and y7 are equal to 1, then w is equal to 1, so that it will be added to the objective function with a negative coefficient to make sure that the cost goes down to 1500 rather than 2000. Can you think about this? So what we have here is, let me write it here. We'll have this W, then I'll have Y5 and Y7, okay? How many different combinations we will have? How many different combinations we'll have here? W is 0 or 1, Y is 1 or 0, y5, y7 is also 0 and 1. If you have 3 decision variables, binary, all of them, each of them can be 0 and 1. So in total, the number of combinations is equal to 8. I explained this in the workshop last week. 2 to the power 3, which is equal to 8. So 0, 1. I want to see which ones can happen, which ones cannot happen. Okay. So when this is 1 and this is 1, what should be the value of W? When y1 and y7 are equal to 1, then W should be equal to 0. This should be happening. This one, this is 1. This can't be 0. Okay? What else? I don't have enough space to write it here. So W, y5, and y7. If this is 0, this is 1, then W should be equal to 0. When this is 1, but this is equal to 0, W should be equal to 0. When both of them are 0, then W should be equal to 0. 1, 2, 3, 4, 5. I have 3 more to write. Okay. But you can write them. These are essentially the ones that we have to make sure that they are there. Okay. Now, you can see from these ones that if one of them is equal to 0, then W should become equal to 0. And if both of them are equal to 1, then W should be also equal to 1. Someone wrote the chat box that I saw. W5 plus W, Y5 plus Y7 should be greater than or equal to W. Does it work with this one? If you write it this way, I mean this way. This one is also going to be satisfied. So this constraint doesn't work. Here you can't do it with a single constraint. First, you have to make sure that when W7 is equal to 0, W is equal to 0 as well. Okay? When this is 1, now W can be 1, it can be 0 as well. Okay? The only thing is I want to make sure that when W7 is equal to 0, then W is equal to 0. When it is 1, then it depends on other constraints as well. I also make sure that when y5 is equal to 0, W is equal to 0. Still, I don't have the constraints, or I don't ensure that when y7 and y5, both of them are equal to 1, still W can be equal to 0, right? When y7 is equal to 0, W is equal to 0. It is forced to become equal to 0. When y5 is equal to 0, then W is forced to become equal to 0 again. But when both of them are equal to 1, you can see that, or one of them is equal to 1, and still you can see that W is not forced to become equal to 1. Okay? Let me see the chat box. Where do I have? Okay. Now we have to add another constraint to make sure that when these two are equal to 1, this W is forced to become equal to 1 as well. So someone wrote as y5, the left hand side is written, but the right hand side is not there. So almost it is correct. I can see that someone else also wrote it. So Advait wrote it correctly. That's very good. So you can see here when this one is equal to 1, this one is equal to 1. Essentially, this is y5 plus y7 is less than or equal to 1 plus W, right? When this is equal to 1, this is equal to 1. Based on these two constraints, still W can be equal to 0. Now, when you have this one, the left-hand side is equal to 2, less than or equal to a summation of binary stuff. So the summation is also at least equal to 2. 1 plus W is equal to at least equal to 2. So W becomes equal to 1. Okay? So these constraints alone, they only make sure that when y is equal to 0, then W is also equal to 0. But they don't enforce the fact that when these two are equal to 1, W should be also equal to 1. At least 5 boxes should be produced. This is, I guess, easy for you guys. y1 plus y2 plus y till y5 should be greater than or equal to until y7 should be greater than or equal to 5. This is what we want. Okay. And finally, we have the decision variables that x, I, z, I, j are non-negative. Y, I, and w are binary. Y is from 1 to 7. J is from 1 to 7. Also, we know that I is greater than or equal to j for Zij, because this is the one that we're going to use another box to satisfy the demand of another box. I should be greater than j, and both of them are between 1 and 7. And we know that Zij is equal to 0, oops, when the other way around happens, right? We can't have z here, z, I'm writing at the top because I don't have space. When zi, for instance, z2, 1 is equal to 0. You can't use 2 to satisfy demand of box 1. This is equal to 0. But z1, 2 is allowed. It can be a positive value depending on the optimization problem that we have. Okay? Any questions? You can ask at the very end as well, so don't worry if you want to ask question at the end. Now, as I said, so let me answer this. Why Zij when j is greater than I? When I is greater than j should be equal to 0. If you go back to this one, the very start of the here, it says that you can use a larger box to satisfy demand of a smaller one, right? So 1 can be used to satisfy 2, 3, 4 until 7, but 2 cannot be used to satisfy demand of 1. 3 cannot be used to satisfy 2 or 1, so on and so forth. And here Zij is box I which is used to satisfy demand of j. Essentially saying that when I is 2 and j is 1, this should be equal to 0 because you cannot use 2 to satisfy demand of j. 1. Z3, 2. Z3, 1. These are also equal to 0. You can't use 3 to satisfy demand of 2 or 1. It goes on till the last one, 7. You can't use 7 for 7. 7, 6, 7, 5. It goes on till 7, 1 are equal to 0. You can't use 1, box 1, to satisfy demand of 2, 3, 4, 5, 6, and 7. Here, we have some conditional statements I wanted to talk before we leave. When x and y are equal to each other, if you want to make sure that when y is equal to 0, then x is also equal to 0. Or the other way around, you have to write it as x equal to y. This is something which is very simple. When y is not equal to x, when y is equal to 0, you want to make sure that x is equal to 1. Or y is equal to 0, you want to make sure that x is equal to 1. Then y is equal to 1 minus x. So when this is equal to 0, this becomes equal to 1. When this is equal to 1, this should be equal to 0. If x, then y. So when x is equal to 1, I want y to become equal to 1. You write it in this way. When x is equal to 1, y is forced to become equal to 0. I don't care about the fact when x is equal to 0. Y can be equal to 0, y can be equal to 1 as well. But I want this, when this is 1, I want y also to become equal to 1. So x should be less than or equal to 1. When x is equal to 1, I don't want y to become 1. So x is less than or equal to 1 minus y. So when this is 1, the right-hand side is forced to become 1. 1 minus y is equal to 1. Therefore, y is equal to 0. Some of them we talked about last week. X is equal to z is equal to x and y. So when z is equal to 1, y and x should be also equal to 1. This is what essentially we did in the previous slide. So when z is equal to 1, x is forced to become equal to 1. When y and x are equal to 0, we want to make sure that z is equal to 0. We need this one to be added because when these two are equal to 1, because this is equality, both sides work, right? When z is equal to 1, x and y should be equal to 1. When x and y are equal to 1, then z should be equal to 1. When x and y are equal to 1, these two constraints are not enough. That's why we add the last one to make sure that z is equal to 1. Z is equal to x or y, or the other way around. When y and x are equal to 1, I want z to become equal to 1, or the other way around. So we have to write it this way. So you can see they are slightly different from AND, because in AND, both of them should be equal to 1 to get z equal to 1, but with or, at least one of them is equal to 1. Then z can be equal to 1. Fantastic. On time exactly. 5 past or like 15 minutes. So I'm going to stop here teaching. I will continue recording. Feel free to ask questions if you have. Can we ask questions about the assignment? Not now, because we're just warmed up for the topic. So if you ask at the very end, that would be fantastic. I'll send post an announcement to for the drop-in session tomorrow. But I'm not sure if I can do that. The back pain that started last week on 2 weeks ago on Wednesday, it's getting worse. I can't move properly. So if I get better tomorrow, I will be in the office to do the drop-in session. Otherwise, I will need to cancel it. So I will do it in the morning. Would there be an office hours this week? Yes, I posted it on my WBS. Tomorrow at, I don't remember even the time, but yeah, tomorrow in the morning I'll have the office hours. But as I said, yeah, 10:30 until 11:15. If I could do it, I will. Under what situation we use M? Can we add to conditional statement slide? It depends. So when you have a fixed cost, when you want to make sure that if a decision variable is equal to 0, the other one is equal to 0. And if it is 1, the other one can get a positive value. Then you have to have big M constraint. It's not like these ones. Depending on the constraint or the restrictions that you have, you will decide to have it or not. So this is the one that we have. So this is what we have. The second one, right? The second one, the third one, sorry. If x then y, which means that when x is equal to 1, I want y to become equal to 1. This is very similar to the big M constraint, right? I didn't use BM here because x and y, both of them are binary decision variables. But there are cases that y is binary, but x is integer. Y can be only 0 and 1, but x can be a big number as well. I mean, a number based on the other restrictions that you have in the problem. That's why you have to make sure that x is not less than or equal to 1, but it is x is less than or equal to a number that it can get because it is integer. Therefore, you add the big M there. Okay. Why is this problem considered as mixed integer as well? You're right. It is integer program. You're right. But you remember that there is no harm of having the number of the boxes here. You can make them. You can, because it is amount of boxes. You can consider them as continuous. But when you solve the problem at the end of the day, you will get integer values. So we know that all every continuous every integer decision variable is continuous, but not the other way around. So if you consider them continuous, you will get integer values at the end of the day. But you're absolutely right. You can call this integer linear program. Any other questions? Do you want to ask your question related to the group assignment? Oh, sorry. Do you want to ask your question about the group assignment? Not. What do you mean? I can't recall whether we have constraints with opposite signs. Example, what? We had transportation problem. We had supply which was less than or equal to and demand which was greater than equality. So when the solution is infeasible, when you don't have any feasible solution, apparently there are problems which are infeasible, but for the group assignment, there shouldn't be any infeasible solution. So apparently you made a mistake in putting the constraints. So I guess I answered your question, not transportation problem. You have less than or equal to and greater than or equality. So I don't get what you mean, what we didn't have. And you always can change the sign of a decision, a constraint. If you remember from last week, I showed you when you have x less than or equal to 2, you can multiply both sides by -1. So it becomes minus x greater than or equal to -2. Okay, so they are the same. If you want to change the sign of a constraint, you can simply multiply both sides by -1. I'm going to stop the recording. Let me see. Do we need to put signs in the Excel? We read to Python. As I said, transportation problem is a good example of this problem because you give the model. I know from the model this constraint should be less than or equality. So there is no need that you put it. But if you put it in Excel, there is no harm with it. As far as it doesn't ruin your data set. Because it's a sign, it's not a number. Can I just write data frame in Python representing the data instead of Excel? You did everything in Python and did not create Excel file. No, I'm afraid no. You have to create the data. That's the whole point of the assignment. You could write them manually, and we don't want to do that. You have to create the Excel file and then import it to Python. Work with your group mates. If you shouldn't be working alone. So, can you please advise with Excel import format you prefer us to use for the assignment? A coefficient matrix format. It's up to you. So we had two different examples. For the paint problem, it was constrained on the right-hand side that we had, but for transportation problem, it was different.
Depending on the problem that you have, you may come up with different sort of data sets. As far as it is clear and understandable by the reader, myself, or anyone else, there is no problem with that. As I said, if you look at my example that I gave you in the brief, you can see that I wrote the model on the top, and then you have the code. There are codes, etc., where you can see x1 plus x2 is less than or equal to whatsoever. So I see it is less than or equality in the model that you wrote. You have to submit the model as well. So from the model, I can see if it is less than or equal to or greater than or equality.